Welcome to this scientific lecture on the Microreactor Unlimited Reactions paradox. Today we're going to explore one of the most fascinating phenomena in chemical engineering, how something incredibly tiny can actually outperform something vastly larger. Let me start by stating the paradox clearly. Even though microdroplets are absolutely tiny, often just picoliters in volume, they allow thousands of reactions per second. This seems impossible at first. How can something so small be so productive? Imagine a tiny picoliter reactor, a millionth of a liter, competing against a massive liter-scale batch reactor. Intuition tells us the big reactor should win. But the paradox is that the tiny reactor actually outperforms it. There are three fundamental mechanisms that explain this paradox: rapid mixing, surface area dominance, and short diffusion distances. Let's explore each one in detail. The first mechanism is rapid mixing. In a microdroplet, molecules can mix completely in milliseconds, or even microseconds. You might ask, why does mixing happen so fast in such small volumes? The answer lies in the physics of turbulence and diffusion. The mixing time is proportional to the characteristic length squared divided by the diffusion coefficient. This is a fundamental relationship in transport phenomena. Let me give you concrete numbers. Consider a droplet that's 100 micrometers in diameter compared to a reactor that's 10 centimeters across. The microreactor has a characteristic length of 100 micrometers, which is 10 to the negative 4 meters. The batch reactor has a length of 10 centimeters, which is 10 to the negative 1 meters. The ratio of mixing times is the square of the length ratio. That's 10 to the 1 divided by 10 to the negative 4, all squared, which equals 10 to the 6th power. 1 million times faster, mixing in the microreactor. Think about stirring soup. In a small cup, you can mix it uniformly in seconds with a spoon. But in a giant industrial vat, it might take many minutes or even hours to achieve the same level of mixing. The physics is the same. The second mechanism is surface area dominance. In microreactors, the surface area to volume ratio becomes enormous. How does surface area affect reaction rates? Many reactions occur at interfaces, either at solid catalysts or at phase boundaries between liquids and gases. For a spherical droplet, the surface area to volume ratio equals 3 divided by the radius. As the radius gets smaller, this ratio increases dramatically. For a microreactor with radius 50 micrometers, that's 5 times 10 to the negative 5 meters. The surface to volume ratio is 3 divided by 5 times 10 to the negative 5, which equals 60,000 per meter. That's enormous. Compare this to a batch reactor with radius 5 centimeters. Its surface to volume ratio is only 60 per meter. That's 1,000 times smaller than the microreactor. Visualize this. The microreactor has far more surface area per unit volume. Each molecule has much easier access to reactive surfaces. This accelerates heterogeneous catalytic reactions tremendously. Here's a kitchen analogy. If you want to cook vegetables quickly, you chop them into tiny pieces. Small pieces have more surface area exposed to heat, so they cook faster. Same principle applies to chemical reactions. The third mechanism is short diffusion distances. Molecules don't have to travel far to find reaction partners. How long does it take for a molecule to diffuse across a microreactor versus a batch reactor? Let's calculate this precisely. Diffusion time equals the distance squared divided by the diffusion coefficient. This is Einstein's famous diffusion equation. For a typical small molecule in water, the diffusion coefficient is about 10 to the negative 9 square meters per second. For the microreactor with length 10 to the negative 4 meters, diffusion time is 10 to the negative 8 divided by 10 to the negative 9, which equals 0.01 seconds or 10 milliseconds. Very fast. For the batch reactor with length 10 to the negative 1 meters, diffusion time is 10 to the negative 2 divided by 10 to the negative 9, which equals 10,000 seconds. That's almost 3 hours. Think about dissolving sugar. A tiny grain dissolves almost instantly, but a large sugar cube takes much longer because molecules must diffuse from deep inside the cube to the surface. Distance matters enormously. Now let's see what happens when we combine all three mechanisms together. This synergy is remarkable. What is the overall throughput advantage of a microreactor? We need to consider both the reaction rate enhancement and the ability to parallelize. The reaction rate is proportional to 1 over mixing time times the surface to volume ratio times 1 over diffusion time. All three factors multiply together. The mixing advantage is 1,000,000-fold. The surface area advantage is 1,000-fold. The diffusion advantage is 100,000-fold. Multiply them, 10 to the 14th. That's 100 trillion times faster per unit volume. But wait, you might object. The microreactor is much smaller in volume. How can it compete with the total throughput of a large reactor? The volume ratio is 1 liter divided by 1 picoliter, which is 10 to the 15th. So the batch reactor is a quadrillion times larger. The answer is massive parallelization. We can run millions or billions of microreactors in parallel. Imagine millions of tiny droplets, each one a complete reactor, all operating simultaneously. Each droplet performs reactions incredibly fast. Together, they achieve massive throughput. If we fill 1 liter with picoliter droplets, we get 10 to the 15th droplets. The total throughput is 10 to the 15th droplets times the enhancement per droplet. This is where the magic happens. Here's a perfect kitchen analogy. Imagine you need to bake 1,000 cookies. Would you use one giant industrial oven or 100 small countertop ovens? The small ovens heat up faster, cook more evenly, and you can stagger batches. Despite being tiny, many small ovens can outperform one giant oven. Now let's talk about practical applications. Where do we actually use this paradox in real chemical engineering? First application is drug discovery. Pharmaceutical companies need to test thousands of chemical reactions to find promising drug candidates. Microreactors allow them to screen massive libraries quickly using minimal reagents. Second application is nanoparticle synthesis. Making uniform nanoparticles requires precise control of reaction conditions. Microreactors provide that control because mixing is fast and uniform. Third application is dangerous chemistry. Some reactions are too hazardous to run in large batches. But in a picoliter droplet, even if something goes wrong, the amount of energy released is minuscule. Safety through miniaturization. Let me walk through a quantitative example. Suppose we want to screen 1,000 different catalysts for a particular reaction. We have 1,000 catalysts to test. In a traditional batch reactor, each test requires 1 microliter of reagents. Each batch test takes 1 hour, including mixing, reaction, and analysis. Total time for batch testing is 1,000 hours, which is 42 days of continuous operation. That's more than a month. In a microreactor system, each test requires only 1 nanoliter. That's 1,000 times less reagent. Each microreactor test takes only 10 seconds because mixing and diffusion are so fast. We can run 100 droplets in parallel simultaneously. Total time is 1,000 tests divided by 100 parallel reactions times 10 seconds each. That's just 100 seconds, less than 2 minutes. From 42 days down to 2 minutes. Let's also consider the economics. How much does each reaction cost? Suppose your reagent costs $1,000 per liter. This is typical for specialized pharmaceutical compounds. Each batch test costs 1 microliter times $1,000 per liter, which is $0.001, or 1/10 of a cent. Each microreactor test costs 1 nanoliter times 1,000, which is 1/1,000,000th of a dollar, 1,000 times cheaper per test. For 1,000 tests, you save almost $1 in reagent costs. But more importantly, you save 42 days of time, which is worth far more in a commercial setting. There's another crucial advantage we haven't discussed yet: heat transfer. Microreactors excel at removing or adding heat. Heat transfer rate equals the heat transfer coefficient times surface area times the temperature difference. The key is surface area. Because microreactors have such high surface-to-volume ratios, they can add or remove heat almost instantaneously. This prevents hotspots and runaway reactions. The thermal time constant is proportional to length. Smaller reactors equilibrate thermally much faster. A 50 micrometer droplet reaches thermal equilibrium in milliseconds. A 10 centimeter reactor takes minutes or hours. This difference is critical for exothermic reactions that generate heat. Think about cooling coffee. A small espresso cup cools to room temperature quickly. A huge coffee urn stays hot for hours. Same physics applies to chemical reactors. Now let's be honest about limitations. Microreactors aren't perfect for everything. What are the challenges? Challenge 1 is clogging. If your reaction produces solids or has any particulates, tiny channels can clog instantly. This is a major practical problem. Challenge 2 is scale-up. Moving from one microreactor to millions of parallel units introduces engineering complexity. How do you distribute fluids uniformly? How do you collect products efficiently? Challenge 3 is that not all reactions benefit. Slow reactions that are limited by chemical kinetics, rather than mass transfer, won't see much improvement in microreactors. Challenge 4 is cost. Microreactor systems with precise fluid control, temperature control, and analysis equipment can be expensive initially, though they often pay for themselves through reagent savings. Let me summarize the fundamental scaling laws that govern this paradox. These are universal principles. Mixing time scales with length squared. Halve the size, quarter the mixing time. Surface to volume ratio scales inversely with length. Halve the size, double the ratio. Diffusion time scales with length squared. Halve the size, quarter the diffusion time. Thermal time constant scales linearly with length. Halve the size, halve the thermal equilibration time. Notice that all 4 fundamental scaling laws favor miniaturization. This is why the paradox exists. Physics fundamentally rewards smallness for transport-limited processes. There's one more important equation we should discuss: pressure drop in microchannels. The Hagen-Poiseuille equation tells us that pressure drop equals 8 times viscosity times length times flow rate, divided by pi times radius to the 4th power. Notice that radius is to the 4th power in the denominator. This means pressure drop increases dramatically as channels get smaller. If you halve the radius, pressure drop increases by a factor of 16. This is a significant challenge for microfluidics. The solution is to use many parallel channels, each with a diameter that balances pressure drop against the benefits of miniaturization. Typically, this optimum is around 50 to 200 micrometers. Let me give you a beautiful real-world example: photochemistry and microreactors. In photochemical reactions, light must penetrate into the reaction mixture, but the Beer-Lambert law tells us light is absorbed exponentially with depth. Intensity equals initial intensity times E to the negative alpha times path length, where alpha is the absorption coefficient. In a large batch reactor, only the outer few millimeters receive significant light. The interior is dark. This severely limits photochemical efficiency. But in a microreactor with path length of 100 micrometers, the entire volume receives strong illumination. Every molecule has equal access to photons. This dramatically increases reaction rates. Visualize this. The batch reactor is mostly dark inside. Only the outer edge gets light. The microreactor glows uniformly throughout its entire volume. Every molecule is activated. Here's an important question. What about residence time distribution? In chemical engineering, we care about how long molecules spend in the reactor. In batch reactors, all molecules have exactly the same residence time because they all enter and leave together. In continuous microreactors, if designed properly with high flow rates and small diameters, we can achieve nearly plug flow. This means all molecules have very similar residence times with minimal dispersion. The Piclet number equals velocity times length divided by diffusion coefficient. High Piclet numbers indicate plug flow dominates over dispersion. Typical microreactors have Piclet numbers around 1000, indicating excellent plug flow behavior. This gives very narrow residence time distributions. Let's discuss the key dimensionless numbers that characterize microreactor performance. Reynolds number equals density times velocity times length divided by viscosity. It characterizes the flow regime. Microreactors typically operate at Reynolds numbers below 100, meaning laminar flow dominates. This is actually advantageous for predictability. Damkohler number equals reaction rate constant times residence time. It compares reaction rate to transport rate. When Damkohler number exceeds 1, reaction is faster than transport, so improving mixing and diffusion has huge benefits. This is where microreactors shine. What does the future hold for microreactor technology? There are several exciting research directions. First is 3D printed microreactors. Additive manufacturing allows custom geometries optimized for specific reactions. Imagine printing a reactor specifically designed for your molecule. Second is artificial intelligence-controlled optimization. Machine learning algorithms can explore thousands of reaction conditions in microreactors and find optimal parameters automatically. Third is integration with online analytics. Combining microreactors with mass spectrometry or NMR allows real-time reaction monitoring and closed-loop control. Fourth is biological applications. Microreactors are revolutionizing cell biology, allowing single-cell studies and high-throughput screening of cellular responses. Let me summarize why small beats big in chemical reactors. This is the heart of the paradox. All transport processes, including mixing, diffusion, and heat transfer, scale favorably with miniaturization. The smaller you go, the faster these processes become. Surface area to volume ratio increases dramatically, enabling faster interfacial reactions and better heat transfer. Massive parallelization compensates for the small individual volume. Millions of tiny reactors working together achieve enormous total throughput. Improved safety, because even if something goes wrong, the tiny volume limits the magnitude of any accident. Precise control over temperature, concentration, and mixing enables optimization that's impossible at large scale, where gradients and inhomogeneities are unavoidable. Let me leave you with one final comprehensive kitchen analogy that ties everything together. Imagine you want to cook the perfect meal. You have a choice between one enormous industrial kitchen with giant equipment or 100 tiny personal kitchens, each perfectly equipped. The giant kitchen has a massive oven that takes hours to heat up. Temperature varies by location. Mixing in huge pots is slow and uneven. Quality control is difficult. The tiny kitchens each heat up in minutes. Temperature is uniform. Small pots mix instantly. Every dish comes out perfect. And you can cook 100 different dishes simultaneously. The tiny kitchens win on speed, quality, and flexibility. The only advantage of the giant kitchen is if you need to make one single enormous batch of something simple. But for complex, high-value products, small is superior. This is exactly the microreactor paradox. For high-value chemicals, pharmaceuticals, and specialized materials, thousands of picoliter reactors outperform a single-liter scale reactor. Small beats big because physics rewards miniaturization.